Alright, so here we go where we left off in class. So the direction angles for a vector, it says tells you the angle between the vector itself and like either the x, the y, or the z axis. And so you remember you have your angle formula from the angle between two vectors here. And so this should not have a 1 right there, and neither should this right there. So anyway, here we go. So this is just basic. You can see how it's the angle between the vector itself, A, and then I. I is representing the x-axis, because remember, I is going to be a vector in the direction 1, 0, 0 from last time. So it's going to give you the direction of the x-axis. And so when you do that, if you imagine dotting this vector with that vector, the zeros will cancel out these two, so you'll get 1 times a1. So that's why this thing ends up with just a1 on top. So basically that's saying it's going to end up with the x value of your vector up top. And on the bottom, well, the magnitude of this I vector, so imagine you had this vector right there and you're doing the magnitude of it. Well, it's only 1 unit long, so the magnitude of that is 1. So if you are going to multiply the magnitudes together, basically you just have the magnitude of A itself. All right, and so that's the formula. That would be the angle that your vector makes with the x-axis. And so similarly, if you have cosine beta, beta is the one with the y-axis, and so instead of having, you'll have a dot j, so j would be the vector going in the direction of the y-axis, and on the bottom you'd have magnitude of A, magnitude of J. Well, remember J is this vector, 0, 1, 0. So if you dot A with that, so A being this, with that one, you're only going to get A2. So you get A2 over, the magnitude of J is also 1, and then you have that A on the bottom. Okay, so then when you have cosine down here for your gamma, for your z-axis, you get A dot K over A and K, and so you end up with A3 and magnitude of A. Okay, so you know, no big deal. It's just some formulas. It's just like using this old cosine formula. So actually, let's go ahead and do. We're going to skip this for a second and then go down to the next one. Find the direction angles, or the cosines are called, of this. So basically, what we have to do if we want to find the first one, we just know that the cosine with the x-axis, alpha, is going to be -2 over the magnitude of this vector right here. So the magnitude of this vector, I would square everything, so 4 plus 1 plus 25, so that would be 30, so square root of 30. All right, so then just grab your calculator and make sure it is in degrees, and I would just do second cosine of, -2 over radical 30. Okay, so 111.4. So I'm just going to give you the answers to the rest. All right, and cosine with the y-axis is going to be 1 over the radical 30, and cosine the gamma here with the z-axis is 5 over radical 30. So in those two cases, beta comes out to 79.5, and gamma comes out to 24.1 degrees. Okay, all right, so if you had to, you could also use these equations to come up with the following conclusion up top here. So basically, if I go ahead and I want up here to get like A1, A1 would be equal to magnitude of A times cosine of A. So I'm going to write that in right here, magnitude of A times cosine of A. And here, A2 would be equal to magnitude of A times cosine of B. And similarly, magnitude of A, cosine, gamma. All right, so just rearranging those three things right there, and then pulling out the magnitude. And so I have cosine alpha, cosine beta, and cosine gamma. I can't draw gamma. Well, whatever. That says gamma there. All right, so now, so this is all equal to A, right? And so if I divide this magnitude of A on the other side, remember that's going to be a unit vector in the direction of A. All right, I could say it's equal to cosine of alpha, cosine of beta, and cosine of gamma. Okay? All right. So that's just something you can do with it. So if you want a unit vector and you know the angle that your vector makes with each axis, which is kind of rare to know, then you can do that. All right, so go ahead and skip over this one here, and I'll make sure that nothing's in the homework that hurts you there. All right, so projection. So maybe you learned a formula for projection in pre-calculus, but we are going to go ahead and do it here too. So again, just a formula, so it's, you can understand the physics of it or not, but the projection vector, you have this is red, the projection of B onto A. So think of projection as like a shadow. So what's happening is you're trying to go this way, and you need a way to break up your vector into two parts that are perpendicular to each other. So the projection vector is the amount of the amount that your vector is going in the direction of the surface you're coming off of. So you're on this surface right here, and your vector is going up off of it. And so the projection vector right here is the part of the vector that is traveling along the surface that you were on. And then you could subtract these two vectors to figure out the third one. We won't really have to do that much. But anyway, there's a formula for the projection vector right here, and it goes like this. The projection of B onto A is, and well, it's actually down below as well, but it goes like this. You do the dot product of the two, A and B, over the magnitude of A squared. So it's basically like the magnitude without the square root part, and that's like your coefficient. And then you have vector A right here, because the projection is the vector that goes along A. So this part is just calculating like the length of the vector, and then you're multiplying that by A. Okay. All right, so let's see down here. Something called the scalar projection, or also the component of B along A, is just basically going to be the signed magnitude of the vector projection. So it's going to take this projection formula, it's going to be a little bit easier, and it's basically going to be the part that's giving you the length of it. All right, so we're going to calculate those two things down here, and I have them right here. So it's important to denote that you say this of B onto A. Okay, so the projection vector is the whole vector itself. So this equals a vector, and this one right here equals a scalar. Okay, so we're just going to calculate those two things here. So we are doing the projection of y onto x, or the component of y onto x right here. All right. So let's see, where are we? So let's see, I'm going to do my projection first. So y onto x. So this is like here B onto A. So this is my main vector that I am staying on. And so I will always know that whatever the length is here, I will have x right there. Okay, so up top here, I just dot them together. And on the bottom, you take this x over here, and you're doing the magnitude of that thing squared. So basically, you're using this vector all over the place, except right there for the dot product. So if we dot these two together, 3 times 2 is 6, plus 3, plus -4. So 9 negative 4 makes 5. So I have 5. And the bottom, the magnitude of x squared. So the magnitude of x would be the square root of 9 plus 1 plus 1, so 11, square root of 11, but I'm squaring it, so that's going away. And so then I have x right here, 3, 1, 1. So if you wanted to multiply it out, you could have 15 over 11, 5 over 11, and 5 over 11. Okay? All right. So up here, your component, so we're going to be using this formula right there. So we're going to dot the two together up top, x dot y. And let's see, over magnitude of x. So basically you can kind of see it's similar to what's here, some pieces missing, but my dot product, I already had that earlier, was 5, right? And we already did the magnitude earlier, that's just the square root of 11. Okay, so this right here is the length of the projection vector. So the component gives you the length of this vector right here. So if you calculated the magnitude, the length of this thing, let's see, the square root, if I square this, so that's 225 over 11 squared plus 25 over 11 squared plus 25 over 11 squared. So I would end up getting 11 squared on the bottom. If you add these together, what's that? 275, right? So 275, right? Yeah, okay. So if I do the square root, so I have the square root of 275, and then 11 squared square root would be 11. So if you rationalize this right here, it will turn into that, okay? Right? Let's see, multiply by radical, yeah. Because 275 is what, 25 times, let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. No. 275, no. Yeah, so that's 11 times 25, right? So 275 turns into 5 radical 11 over 11, right? So you can see how it's the same thing. Okay, so anyway, the component vector here is just the component is just the length of the projection vector. All right, let me just do like, let's see, a couple more minutes here. We'll finish this up. So my work is, one use of projection occurs in physics when calculating work. The work is done by a constant force moving an object a certain distance, and you have the angle with which the force is applied. And so you have two different situations here. So here's your work if you know the force and the distance and the angle right there. And so let's go ahead and do this example right here. So in this guy right here, my work done is going to be the force I'm applying, 70 newtons of force. So I got 70. I'm doing this for 100 meters. And the angle we are pushing at is 35 degrees. Okay, so your work there, if you multiply it out, you will say 5,734 joules, or you could also say Newton meters. Okay. And over here, the other thing that you can get from the other format of this right here, so these are two formats of work, and that's if you're just given the actual vectors there. So your work can also be the force vector and the direction vector right there. Okay, so your force vector, 3, 4, 5, dotted with your direction moves from this point to that point. So I need to find this vector right here. So 4 minus 2 is 2. 6 minus 1 is 5, and 2 minus 0 is 2. So I'm dotting that with 2, 5, 2. Okay, and so that comes out to 36 joules. Right. And that is it. The work formulas aren't that big a deal. I mean, it's either just going to be given to you this way or that way. You don't have to like develop the formulas or anything like that. Okay, I'll see you in class. Bye-bye.